All right, now let's talk about specific technologies and what do they contribute to the unloaded quality factor. Now that we understand how the quality factor is affected by volume, how it's affected by surface area, and what its impact is. So first of all, let me talk about the lumped element resonators. So that means that you literally take discrete capacitors and inductors to build your filter. When you make that choice, the great thing about that choice is that everything will be really small. In fact, you can even integrate inductors on the substrate and make everything very tight, very confined in the system that you have. But by making that choice, you're limiting the volume where you can store the field, and you're increasing the surface area that has metal that the filter can actually, the field can actually be dissipated. So in general, if you choose relatively large off-chip resonators, you can maybe hope to get something in the order of 100 Q. But if you go for on-chip resonators, it's not uncommon to basically end up with a Q of only 5 or 10. And in extremely good technologies that tend to be actually quite expensive, you may actually go for a Q of 50. So that's why lumped element resonators in general are actually utilized for very forgiving filtering applications. You can't really get quality factors, in the order of 1,000 or above that would be highly desirable in many, many systems. So essentially, you make a trade-off. You make something very, very small, very tiny, but don't expect any high quality filtering out of that. The next best choice is to actually go for a lumped element. From a lumped element to a two-dimensional filter. That's the case we have been discussing here with microstrip or CPW or strip lines. Now we basically make ourselves a little bit better because we give a reasonable volume for the electromagnetic field to be stored, and we limit the surface area of the metal that it can actually be dissipated on. So when we make that choice, we basically go for a two-dimensional resonator. Now my quality factor starts improving. In fact, you can normally get quality factors in the order of maybe up to 200 for most technologies. And if you go for extreme technologies where you optimize things from all points of view, from radiation, from dielectric loss point of view, and this is one example which we'll be discussing later on, then you can actually start approaching Qs in the order of 500. So a very clear improvement from the lumped element case, but of course the cost here is again volume. Things have to be now lambda by 4 or lambda by 8, and so if lambda is pretty large, then maybe this is an unrealistic application. But the good thing is that as your application is scaling up in frequency, these choices become easier to implement because things become smaller. One more step up here is the coaxial resonator. In a coaxial resonator, which is quite common in high demanding applications, like for example in satellite communications, you have a really good platform to work with, because first of all, in a coaxial resonator, you have a large volume to store your field, and you have very low dielectric loss. Because of this nice compromise, that Q now can actually start being in the order of a few thousand, maybe 1 or 2,000. One equation, by the way, that is quite useful to use, and that applies for the microstrip or CPW that I mentioned before, actually for any distributed resonator, is that the quality factor in this case will be equal to beta, which is the propagation constant, divided by 2a to alpha, which is actually the attenuation constant. So another additional advantage of a coaxial resonator is that you basically have practically no radiation. Because everything is now confined in a closed volume, you don't have to worry about losing anything from radiation, which might be the case, for example, in a microstrip or a CPW line if you forget to package it in some good way. Now, the ultimate way of getting a very high quality resonator from electrical resonators is basically to go for a waveguide solution. So waveguide solutions are well known for essentially giving you resonators that have Q in the order of 10, 20, or even 30,000. So this type of waveguides, for example, a circular waveguide or a rectangular or elliptical waveguide, are essentially utilized in high demand cases. So the price here, the penalty, is that the volume is quite large, and the waveguide actually may be heavy if you require a lot of metal to make this structure, for example, if the frequency is low. So you will practically never see this in very low frequency applications, but you will see it in high frequencies. Also, as we're going to see later on, people have been playing tricks to essentially reduce the required volume from a waveguide for an acceptable trade-off of Q. It turns out, for example, that we can take this waveguide here and make a substrate integrated waveguide by substantially limiting its height. So instead of having the full height waveguide, which is what we normally would need, we can basically make the height of the waveguide equal to our substrate thickness. Of course, the penalty is that our Q now will be dropped, but it's still Q can be in the order of 1,000 of structures like this. So you can reduce volume substantially and still get a reasonable quality factor. Also, as several people have been investigating, including my own group, it turns out that you can actually utilize obstacles inside of waveguide to bring the waveguide below its cutoff frequency. Again, this is a trade-off essentially of miniaturization and Q. So you may accept a drop of Q from 10,000 to 1,000, which is still quite good for many applications, and this buys you something in the order of 30 to 40 times reduction in volume, which again can be a very, very desirable outcome.